video, we're going to determine whether there is a linear correlation between two variables. And generally, we're talking about x and y. So generally speaking, if the absolute value of r is close to 1 and the sample size is large, we say there's a linear correlation between the paired data. In this example, we're given that the linear correlation coefficient, which is r, for a sample of bivariate data with a sample size n is equal to 49, is found to be r is equal to negative 0.901. And we want to know what conclusions can be drawn. So there's a few things I would like to look at. So recall our bivariate data is our paired data in x and y. And we could look at our situations that we could have. Perhaps we would have something that looks like this. And so in this case, it looks like that data is pretty close together. And in this case, r is near 1. And drawing that line through that data there, that line is, as we read it from left to right, is increasing. So here we have a positive slope. And there would be a positive correlation. We would say there's a positive correlation between the x and y. So here's x, here's y. In a similar situation, perhaps our paired data looks something like this. And we can say, well, maybe it looks like there's a line that will go through that data. And here in this situation, r is near negative 1. So if r is near negative 1, and comparing that back to our problem here, r is near negative 1, we have a negative slope. And there's a negative correlation. And then I'll just go ahead and look at that last situation. This is again x and y here. Or a third situation, x and y. Perhaps our data are just scattered all over the place. In this situation, r is near 0, and there is no linear correlation here. So we can't come up with that linear regression equation. But in our problem here, we're given that the sample size is n is equal to 49. So that's not a very small sample. And r is negative 0.901. So that's near negative 1. So what we could say, what conclusion can be drawn, we can say, well, r is near negative 1, and thus we have a negative correlation. So that's just loosely speaking. We can be a little bit more technical in the way we approach this problem. And we can look at the absolute value of that linear correlation coefficient. So this is the absolute value of r. Remember, if we put those vertical lines around that number. So if the absolute value of that linear correlation coefficient is greater than a critical value, if that's true, then we can say that a linear relationship exists between x and y. And if r is near positive 1, it would be a positive correlation. If r is near negative 1, then it would be a negative correlation. So we're given the value of r. So that's negative 0.901. I'll put that in absolute value. Now for the critical value, I would need to perhaps refer to a table and look up the critical value. And when I do so, I'm going to use the sample size. In the table I looked up, I chose the closest value to n is equal to 49, which was n is equal to 50. And I found that the critical value is equal to 0.279 for this sample size. And that's also given the parameter of something called alpha is equal to 0.05. This is a table that's in the back of textbooks that you can look up. So I'm going to compare that, the absolute value of R with the critical value of 0.279. And so the absolute value gives us a positive value. 0.901 is greater than 0.279. That is true. So then there is a linear correlation between the paired data. And again, since R is negative, we have a negative correlation. So there's a couple ways we could go about this problem. We can just say, well, it looks like R is pretty close to -1. And so then we have a negative correlation, or we can be a little bit more technical about it and compare it to a critical value and see indeed that the absolute value of the linear correlation coefficient is greater than the critical value, and conclude that there is a linear correlation between this data.